In this video, I'm going to go over the batteries tab. So a battery company advertises that one of their batteries has an average life of 19 hours. One of their engineers believe that they have developed a new version that has an increased lifespan. So they take a sample of these 50 new batteries and they want to determine if the average life is greater than the claimed mean of 19 hours. The sample data is in this worksheet. So we're going to conduct a hypothesis test with an alpha of 0.05 to determine if the average lifespan of the new batteries is longer than the advertised average of 19 hours. All right, so this is a one sample test because we have a sample of the new batteries and we are comparing it to the advertised average life of 19 hours. So that's a one sample test. So now we need to determine if it's a z-test or a t-test. And remember, the difference between a z or a t-test is the population standard deviation. So do we know the population standard deviation for the advertised lifespan? And we do not. So they gave us this population mean of 19 hours, but they have not provided us with a population standard deviation. So that makes it a t-test. Again, we conduct a t-test when we do not know the population standard deviation. Because we're using the t-test, we're conducting a t-test, we are going to use the t-distribution to determine the probability or the likelihood of obtaining our sample mean. All right, before you begin the calculations, you always want to write out the hypotheses. So the null hypothesis is always the same. It's the two groups have the same population mean. So for this example, it would be the average mean battery life for the new batteries is the same as the advertised of 19 hours. So the alternative or the research hypothesis is found in the research description. You can find it over here. We wanted to determine if the average lifespan of the new batteries is longer than 19 hours. So if it's greater than 19 hours or the advertised length. So this makes it a one-tailed right. Again, anytime we predict that sample group is going to be greater than the population mean, that's a one-tailed right. All right, now we can start filling in our calculations. The advertised lifespan, this is the population mean, 19 hours. And then for the new battery, we have a sample. So I'm going to compute the average. And I got an average of 19.34. It said in the research description, this was based off 50 batteries, but let's use the count function. Yes, and we have 50 batteries. All right, we do not know the population standard deviation. We only know the sample standard deviation, right? S equals the sample standard deviation. This is sigma. It's a Greek symbol. I'm just going to put O. That is the population standard deviation. So you need to think about, do you know the population standard deviation or the sample standard deviation? We do not know the population standard deviation. So they gave us this population mean of 19 hours. They did not give us a population standard deviation. So we are going to compute the sample standard deviation. And that's with the standard deviation function for the sample in Excel. And then we'll just select our data. And I got a sample standard deviation of 0.85. All right, now our standard error. The formula for the standard error, you can see it right here. It's the sample standard deviation divided by the square root of the sample size. So this formula usually requires the population standard deviation. We do not know it, so we're going to substitute with our sample standard deviation. And I got a standard error of 0.12. So on average, we expect a sample to differ from the population mean of 19 by 0.12. All right, so now we're going to determine if we should reject the null. So are we going to, when are we going to conclude that the battery life is longer or the battery life is the same? So that's alpha. So alpha is the size of our rejection area. Ours is 0.05 or 5%. And what we're going to do is we are going to put that alpha into the right tail only. So we're not going to have a left critical value, and that's because we're not looking for our sample mean in the left tail. We just predicted that we think the battery life is longer. So we're going to put our alpha, our rejection region, into the right tail. And then we are going to find the standardized score that cuts off the top 5%. This is the t-score. And the formula for that, the function for that is t.inv. And we're going to do 1 minus 5%, and that's because we want the top 5%. And then the degrees of freedom is the sample size minus 1. And I got 1.68. So this is the red rejection region. This is our alpha. It's the top 5%, and it's marked by a critical value, a t-score of 1.68. We can convert that to a raw score. So that is the population mean plus the standard error times the critical value. And I got 19.2. So this is our raw critical value in raw units. So it would be hours. So we're basically saying with this raw critical value that if our sample mean is above 19.2, that's when we'll conclude that the batteries last longer. So what's going on with ours? Well, we got a sample mean of 19.34, so that is above our cutoff. So that indicates that these new batteries do in fact last longer. Let's convert our sample mean to our test statistic. The formula for that, you can see it right here. It is the sample mean minus the population mean divided by the standard error. And I got 2.84. Let's also determine the probability of that. So we're going to do the p-value for a right-tailed test, and that is 1 minus t.dist. When you do a right-tailed test, you just do a right-tailed p-value. When you do a left test, you just do a left p-value. It's the two-tailed where you have to pick. So we're not doing two-tailed, so we're just going to do the p-value for a right-tailed test. And that is the test statistic, then the degrees of freedom. And for this test, it's the sample size minus 1. And then for cumulative, we're going to put in 0. And I got 0.3. So you can see we are going to reject the null. We're going to reject that the battery life is 19, right? Our sample mean is beyond the cutoff, so 19.34 is greater. Our test statistic is more extreme, or it's beyond the critical value of 1.68. And then our percentage is smaller than our alpha. We got 0.3 and the alpha was 0.5%. So you can see we are rejecting that the new batteries belong to this distribution and have a mean of 19. We're going to conclude that they belong to a different distribution and the mean is greater than 19. So this is the p-value approach and the critical value approach. This is just a way to determine if you're going to reject or fail to reject, which we've already discussed, but we'll spell it out. So with the p-value approach, you compare alpha to the p-value. So you're comparing the percentages. So our p-value was 0.33. Our alpha was 5%. Our p-value was smaller than alpha. So we reject. Remember, when the p is low, the null must go. So we're rejecting that the mean is 19. With the critical value approach, you compare just the standardized scores. We did not have a lower or a left critical value. You want to leave this row blank because we did not have one. We only had a right one. So our right or our upper critical value was 1.68. Our test statistic was 2.84. And here they are on the graph. The test statistic is gray. The critical value is red. Our test statistic is beyond. It's more extreme. It falls in that red rejection region. So we are going to reject the null hypothesis. We are rejecting the null hypothesis that the mean is 19. So we found a difference. So you can see that our test statistic is in the right tail. That's greater than. You can see that the sample mean is greater than the advertised. So we found evidence that the new batteries do last longer than the advertised average. And in symbols, it would look like this. So the population mean for the new batteries is greater than that advertised mean of 19 hours. So we got statistically significant results. All right, the last question. So our sampling error is the standard error. Ours is 0.12. So on average, we would expect a sample mean to differ from a population mean of 19 by 0.12. Again, these sample means are normally distributed. This question asks about what is two standard errors. So 68% of samples are going to be within one standard error. So here's the population mean of 19. Here's one standard error, 18.88 to 19.12. Here's two standard errors, 18.76 to 19.24. So 95% of samples are going to be within this range, 18.76 to 19.24. All right, what was our raw cutoff? The raw cutoff was 19.2. Our sample mean was 19.34. The raw cutoff was 19.2. Our sample mean was 19.34. This is greater than that raw cutoff, so that's why we concluded that the batteries do last longer. All right. So the last thing we want to do is we're going to estimate the population mean for the new batteries. So we have the sample mean just based on 50, but now we want to estimate what the population mean is for all new batteries. So we got to compute the margin of error. That formula is the critical value. It's a two-tailed critical value. So that's T dot INV, 1 minus alpha divided by 2. And then we have our degrees of freedom, sample size minus 1. And then we multiply this by the standard error. And then the lower is the sample mean minus the margin of error. The upper is the sample mean plus the margin of error. So we are 95% confident that the new batteries last between 19.1 and 19.58 hours. So again, this was the estimation for all new batteries. And this is how long we think that they last, 19.1 to 19.58. All right, so this is it for the batteries tab.